All right, section 4.3, we are going to look at, this section calls it rules of logs. I don't really like the word rules. I think properties is probably a better description. But we're going to look at different rules or properties of logarithms today. The first one that we're going to look at is simply an idea of inverses. And we didn't actually write this down last time, but we did everything necessary to have created this property or rule last time as well. It says that if you have log base a of a to the x, that equals x. And similarly, a to the log base a of x equals x. And I'd like to just draw the scorpion tail around so you can see why that makes sense, because it's very reasonable that this is a true statement. So if you were to rewrite this and you were to rewrite a to the x, right? A is the base, the part that was circled, around to the x on the other side and land back on top. It lands back on top at a to the x. They're the same. Right? So yeah, you're like, well, of course that makes sense. Again, it's one of those things. If I multiply by 2 and then I divide by 2, I didn't change anything. And the same thing's true here if I were to change this into an equivalent log expression, because this is, I know it says log inside of it. Like I see that there's a log here, but the base is an exponential, right? This is an exponential equation because of a base with an exponent. So if I were to rewrite this as a log equation where this base is now the base of my log, and I were to separate things, I would do the x, and then I would land back on top of what's next to it, which is log base a of x. So again, just by rewriting with the things that we know how to rewrite, obviously this is true. So why is that helpful? Well, it's helpful because if you take a look at these examples, when you notice bases of logs and bases of exponentials matching up, they do in effect cancel one another out. Okay? So what you're seeing happen right here is, what is the base of this log on part A? 10, right? It's a base of 10. So what you really have happening here, let me just rewrite it with that base 10. Is that it looks like this. And the fact is that since you have the log base 10 here and the 10 here, according to the inverse property, these cancel out, and all I'm going to be left with is y plus 1. Okay? So it simplifies things very quickly when those match up. The same thing happens down here on part B. Here's the 7, and here's the log base 7. I realize now this is an exponential raised to a log, where this is a log with a base of an exponential. But the property, is the other property of the inverse property here at the top. This base of 7 here and this log base 7 here, those cancel one another out, and I'm left with simply the 999. So this inverse property is a nice way, when they match up, right, of simplifying things, is what it really is. We have 3 more properties that we're going to take a look at. And these 3 properties mirror some of our exponential properties from before. So if you'll remember when we did exponential properties, let me just remind you of a few that are helpful as we move to the next slide. When we had a to the m and a to the n, what did we do with those 2 exponents? It's been a while since we've done this. We added them. A to the m plus n. When we had a to the m, so this is like, we'll put 1 and 2 on these, over a to the n, right? We subtracted. Y'all remember this? So we're going to do the same kind of thing now, but with logs, where we see things that look like addition and then they become multiplication, or vice versa. Okay? So this is all hinging back on this idea of an exponential properties we've seen before, because there's this unique relationship between exponentials and logarithms. In particular, they're inverses of one another. So the properties look very similar.
Oh, hold on.
A lot of writing for you. So what you see on the first one, again, looks like that I've got multiplication, right? Kind of like it looked like I had multiplication on number 1 down here. And what you see happening is you see it actually look like we're separating it into two log expressions that are separated with addition. Now, it has to be multiplication on the inside for this to work. So if there's addition on the inside, it doesn't do this. Right? This is a multiplication on the inside property. So multiplication on the inside separates into addition. And if that happens with multiplication, then you might feel much like on those exponential properties that there has to be some sort of correlating idea for division. And there is. If I divide the inside of a log, then I can separate it out as two individual log statements, but they're not subtracted. So these product and quotient rules are very much like the same rules that I wrote on the other screen, where I'm changing addition into multiplication or vice versa, subtraction into division or vice versa. The power rule is a very interesting one here at the end. The power rule makes it look like we have this x right here, this exponent, right, on the interior, and it sort of comes down in front like it's a multiplication factor. That's what it looks like. And really all it is it's a glorified or a simplified maybe example of this log property here. Right? If this said m squared, that'd be m times m, right? That's what m squared is. Well, okay, I can write that as log of m and log of m. Well, what's log of m plus log of m? Well, it's 2 logs of m. Okay? So that's what's happening in this power rule, is that it's just a simplified case, really, of the property for products.
So
yes.
say for the power, you put a 2 there instead of the x. It'd just be 2
exactly.
logs a's and n.
Right, so this is what I was referencing here as well. Yeah, if you had a 2 here and you used property number 1, this is the same as log of m, right? That's what it means to multiply, which we would separate or could separate from part A or number 2 at the above, like this. And sure enough, there's now 2 of them there, so now you see that 2 showing up at the front. And there's nothing special about 2 except that it's easy to use it because I don't have to write a whole bunch of them out.
It kind of gives me chemistry vibes.
Does it? I'm sorry.
So if it's asking for you to do the product, you just stop at that. You don't.
So well, we haven't done any examples with them yet, so hold tight. We're going to have examples that are going to ask us to do 2 different things. They're going to either start with something that looks all condensed, like the left-hand side of these, product quotient power, so the left-hand side over here, and it's going to be all mushed together, and it's going to say expand, and we're going to sort of draw it all out long ways, okay, with a bunch of product, sums and differences and numbers in front. Or it's going to be all drawn out long, like that, and it's going to say condense, and we're going to mush it all back together. So we're going to use these properties to both expand and condense log expressions. In doing so, the reason we're doing it is because it allows us to use things like property number 1 over here, where I can actually do some simplification some of the time because I've either expanded or I've condensed. Okay? So let's take a look at some examples. Did everybody get them written down first? I'm sorry. Yeah? Okay, so this is the part that to me it kind of feels like a puzzle, right? You're kind of breaking things apart. You're kind of moving things back together. So we're going to do part A and part B here with the directions to rewrite as a single logarithm. So rewriting is condensing. We're going to mush it back together. Okay? So this says that I have addition. So I'm going to be using this property where I have addition of logs to push it back together. And the addition of logs, if I read this property from the right-hand side to the left-hand side, says that when I have addition of 2 logs, I can mush it back together using multiplication. So over here, I'm going to have a single log when I'm done, log base 3, but it's the interior of the 2 logs that are the m and the n from the previous slide. And what will I do with them? Yeah, I put them in parentheses next to each other, or I multiply them if I have the ability to simplify something. So you're right. I have, let's see, I have x minus 1 times x. So if you think about it, this is what we sort of have. You can leave it written like that. You don't necessarily need all my boxes and parentheses all going together or whatever. So, but you can leave it like that. Or if you were looking at finding another way to write it, or maybe you were looking at an example that has been done in My Math Hub and you're like, well, where'd they get that from? They might actually distribute this out. You don't have to, but you could. And you could write it as x squared minus x. Now, the goal is to mush it back together as a single log. So it's not like I look at that and say, oh, look, now I have subtraction. I can do something else with it. We're not asked to do anything else with it. In fact, you can't do anything else with it anyway, but we're not asked to. We're asked to rewrite it as a single log, which we have. I have log base 3 of a single expression. Maybe an ugly expression, maybe even uglier than this one sometimes, but it is a single expression. Okay, is that one all right? All right, let's take a look at the next one. The next one's a little bit different, and the reason it's a little bit different is because I have numbers in front of my logs. Does everybody see that?
Yes.
There's a couple of different ways you can handle it. One way to handle it, especially on this one, is to recognize that the values in front are the same, aren't they?
Yes.
So if the values are in front are the same, what you could do is you could factor them out first. So let me show you this option, and then I'll show you another option that works more generally speaking, okay? This works nicely because the numbers are both 1/3. What I see now is the subtraction of 2 logs. Well, the subtraction of 2 logs happens right here. Okay? So I've got what's on the left hand or on the right hand side, and I'm going to mush it back together with what's on the left hand side. So the subtraction of 2 logs becomes a single log with division. So that 1/3 just stays out in front. We'll deal with him in a minute. We will have to deal with him too, by the way. We don't get to ignore him or leave him there. But we will rewrite this then as natural log of 6/2. Now, if you leave that as 6/2, I might just at least pull some of my hair out. Because you can simplify that, right? There is no reason to leave that as 6/2 because it simplifies nicely to 3. So we can rewrite this very nicely as 1/3 natural log of 3. But again, we still really aren't done. What it wants is a single log, not 1/3 of a log. Okay? So if you take a look at this piece at the very end, this 1/3 of the log, I can use that third property on here, property number 4 specifically, the last one on the page. And I can take that 1/3 that's in front and I can pull it back up into an exponent.
Oh.
So it actually could be rewritten as the natural log of 3 to the 1/3. How else could you see it written instead of 3 to the 1/3? Like this, yeah, you could. So this is perfectly fine. We could stop right here and it'd be right. Another option is you might see it written as the natural log of the cube root of 3, because the power 1/3 is a cube root. Again, I don't need you to write it that way, but you could, and it would be correct.
So what way was my math lab?
One more time, Kaylee.
What way was my math
I don't know what my math lab will do on it. I'm not sure. I have a feeling they'll accept the 3 to the 1/3 just fine. But if I'm wrong, then it's because they're wanting you to put in that radical form, and now you'll know. Yeah.
So lame.
Okay. Now, again, that was really nice because it happened to be the case that they were both a power 1/3 in front, right? Like the coefficient was 1/3 in front. And I said, that's kind of specific. I can do this factoring out thing. But generally, what happened if one of them was 1/3 and the other one was 6? You know, or 1/7? I mean, what would you do then? You couldn't just factor something out in front and proceed. What would you do? So let me show you what you would do in general if they didn't match up. If they didn't match up, you would take each of those coefficients and you would make them powers at the beginning. So you would write this as the natural log of 6 to the 1/3 minus the natural log of 2 to the 1/3. Okay? So instead of doing the power part at the end, you do the power part at the beginning because that allows you to have single log expressions. And when I say single log, I mean log with a number 1 in front. And now I have to combine them so that there's only one of them instead of 2 separate ones with subtraction.
So would you still the 6/2?
You would, but it'd be 6 to the 1/3 over 2 to the 1/3. I'm going to give myself a little bit more structure. Sorry about that. Again, because these have 1/3, if we'd gone this direction, we would have still needed to simplify the 6 to the 1/3 and the 2 to the 1/3. Like, we have to do that. That's not an option. We would have to keep going. In general, if they didn't simplify, we wouldn't need to worry about it. But what'd you say, Maxwell?
Don't the exponents just cancel out?
They do not, unfortunately, but they can factor out. So I can write this as 6 over 2 all to the power 1/3. That's a property of exponents. That says if they have the exponents match, I can factor them out. And you can see how we're now back at the same place we were before, right? So this is natural log of 3 to the 1/3, or the natural log of the cube root of 3. So it doesn't always have the ability to clean up so super nice, right? We might have actually been stuck back here if there wouldn't have been a simplification there possible. And I'm pretty sure we'll see another one of those later on, so
My hands are sweating.
no fret. Okay. Oddly enough, I didn't even see those examples in my notes at all. Isn't that fun? Okay. Oh yeah, I do. I was just already on the next one. Okay, cool. All right, here's C on the same direction set, rewrite as a single logarithm. There are 4 logs here. But you know what? It doesn't matter. It's the same rule, just 4 times instead of once, right? Well, 3 times instead of once. I'm combining with multiplication and division based on whether or not it's addition or subtraction. Now, here's the kind of cool thing. We do notice on this one that some of them have coefficients and some of them don't. So much like on my alternate, option over here, the second way I did this problem, I said, oh, let's just move those powers up first. We have to do that on this particular problem because some of them have coefficients and some of them don't, and the coefficients don't match. So that is my first step. My first step is to get all the coefficients to be written as powers. So the first one doesn't have one, so it's just log 2. The second one doesn't have one, so it's just log x. However, on the third one, this 1/2 has to move up. So this is plus log of y to the 1/2. And then the last one has a 3 here, so I'm going to have minus log of z to the 3rd. Is that step okay? Just the shift of the coefficients to make them exponents. If you don't like that written as y to the 1/2, how else could you write it? No, not -2. Good guess. What's a power 1/2 equivalent to? It's a square root. So the log of the square root of y. So I'm going to write it that way because they're a little bit more familiar to us than those funny exponents that look like fractions. So I'm going to go ahead and write it that way. If you choose to leave it the other way, that's fine with me too. So either of those 2 versions have log with a coefficient of 1 now, right? Yeah. So what that means is it means that properties 2 and 3 over here, products and quotients, apply. So it means I can take things that are all branched out, like on the right-hand side, and I can mush them back together. And I do that with addition, the addition corresponding to multiplication, the subtraction corresponding to division. And the cool thing is that I've got a bunch of addition and subtraction here, but the sign in front tells you what to do with it. These 2 tell me that those are both going to be in the numerator because they're added. There's a plus sign here. That square root of y also going to be in the numerator. But the subtraction sign here means that that z cubed is going to be in the denominator. So as I rewrite this, this will have log, single log. Don't rewrite your log. 1 log. It will log, nothing else rewritten. Okay, so this is not log divided by log. It's just log. The 2 will go on top. The x will go on top. And the square root of y will go on top while the z cubed goes on bottom. All the pieces that are added go on top. All the pieces that are subtracted go on bottom. All in one step. Okay? See See, it's like Pig Latin or, some code game you played with your friends when you were in middle school, right? It's just codes. You're just rewriting pieces of things with a particular property. Okay, so we've spent 3 problems where we have taken things that are all branched out and we've mushed them back together, right? Now we're going to do some problems where they're all mushed together and we're going to branch them all back out. Okay, we're going to expand them. So the directions say something like this. Rewrite as a sum or difference of multiples of logarithms. So what does that mean? Well, it means that the interiors better not have any multiplication or division, and it means they better not have any exponents when I'm done. So the first problem, part A. What operation is happening inside of the log, right, in that parentheses that I need to expand? It's the division, okay? Now, the addition that's happening in there, I don't have any properties to do anything with it. I only can do things with division or multiplication or powers. So the division can be separated, but not the addition. So when I'm done, I will have the natural log of 2 different pieces that are subtracted, right? Because there's division. Well, the top is a plus b, and the bottom is a. And I know that some of you desperately want to sort of like distribute the natural log through the beginning or something like that. Remember, distribution is a property of multiplication over addition subtraction. Natural log is not a multiplication number. It's not a number being multiplied. It's an operation. What you want to sort of think about is more like, hey, I've got the square root of a plus b, kind of like this, and I've got the square root of a, but I can't combine them because they're radicals and they're different. The same's true for logs. They're logs and their interiors are different. There's no way to combine them. So the thing is that we're done right here. There is no more simplification or no more expansion or breaking apart that I can do. There is nothing else.
I got a question.
Yep.
In the real world, like, what are logs used for?
Logs are used when, well, we'll do some applications. So hold tight to that. I think the applications don't come in section 4.4, but we do some applications with logs. Maybe it's not in 4.4. Maybe it's in 4.5. I don't remember. There's applications where you're looking at solving different types of exponential equations, things that grow exponentially. So remember we did applications with compound interest? Mm-hmm. Well, your calculator can solve equations without actually mathematically manipulating it, right? You can do things with graphs and stuff like that. But in order to solve them mathematically, algebraically without a graph, logarithms are needed. So you can use application problems that involve exponentials and things like that to do that.
Money.
Yeah. And for example, so my business calc class, they meet in here after you guys, right after this. And one of the models that they do is a logarithmic model. And so they model things logarithmically. So we use very specifically natural logs when we work with that class, but you can use other logs as well. Yeah. Okay. How about the next one? What are some things you notice on this one that need to be broken down? The division part. What else? The exponent part. Both of those pieces can be broken down. Now, if you're super ambitious and think you can keep track of it all at the same time, you can do it all at the same time. That's fine. I'm going to do it in 2 steps. I'm going to do the division first, okay? Because the division actually separates the 2 larger pieces of what's going on. So this one's an actual log, like a common log. So I have log of the first piece, what's on top, minus the log of the second piece, which is what's on bottom. Okay, so I'm just taking the division and I'm separating into subtractions. Everybody good so far? Awesome. And then we're going to deal with the exponent, and we're going to take the exponent and bring it down. So I now can bring down my negative x log of 3, and then minus the log of 4. And that's the fully expanded version for that one. Okay. C feels funny. What operations do you see on C? Division and multiplication, but where's the multiplication occurring, Megan? The multiplication happens on the bottom, right? Does everybody see that?
So does that mean we don't do anything with it?
Well, what it means is that we really have division by two values. There's a division by 2 and there's a division by y. Does that make sense?
Become separate.
They will become separate pieces, but they will both be subtracted. I know that the y and the 2 are multiplied, but they're multiplied inside of the denominator. And the denominator pieces are understood to separate with subtraction. So as I separate these out, I do have log base 2. I have log base 2 of 5, and then I'll have minus log base 2 of 2, and another minus log base 2 of y. Because the 2 and the y are both in the divisor, right? They're both being divided, or they're both dividing the value 5 on top. Now, there's one more thing I can actually do on this one. And it isn't.
Can you subtract the log base 2?
I can't subtract. What do you? It's a little bit further, Bailey. What do you mean subtract the log base 2?
Well, like the 5 and the 2.
No, you can't do that. That's a good idea, but you can't do that because they don't match perfectly. Damaris, do you have another thought?
No, that was what I thought.
Okay.
Just why? Oh, wait,
Okay, I want you guys to flip back to the very first property we had, property number 1.
Are there lots of answers?
Yes, they do. Which one do you see that does that, Megan?
All three of them?
Not all 3 of them. There's just one of them
Oh,
that
you can
cancels.
combine 5 minus 2.
Nope, can't combine the 5 minus 2.
The 2 and the 2.
Okay, so Kenny, you got the right one. This one right here is the very first property that we saw. The very first property that we saw says that when the log's base 2 and what it's taking the base of 2, that there's a cancellation that go on. And what happens is I'm left with the exponent. What's the exponent right here? That's not a 0, that's a placeholder. What is it?
1.
It's a 1. There's a 1 right here. Okay? So property number 1 says, let me shift this up just slightly. Says there's nothing I can do with the log base 2 of 5, but because this 2 and this 2 match, all of this will cancel and will leave me with the exponent 1. Minus the log base 2 of y.
So if we have something like that, we're supposed to do the other way.
You mean like mush it back together the
Yeah.
other way? They would be already written in logs, so you wouldn't have to happen. It wouldn't start out looking like that. It wouldn't start out looking like that.
Like that means all like math
Yeah,
problems.
Damaris.
I'm just confused on how we got the middle term, the log 2, where that came from, because I understand obviously the log 2 and the 5.
So we separated 3 pieces. The 3 pieces that we separated are the 5, the 2, and the y.
Oh, okay.
So they separate into 3 logs because it's all multiplication and division going on. The reason that the 2 and the y both become subtraction is because they're both in the denominator. But that's where the 2 comes from, is from the 2 in front of that y.
Okay.
Okay, so I was just sort of chomping at the bit last time to want to be able to help your calculator to simplify certain things. Remember that? And I kept saying, oh, I think I can. No, I can't. And Maxwell's up here saying, my calculator can do it. I figured it out. All right, so I'm going to show you how your calculator can do it too. Are you ready? All right, we have a property called the change of base formula. And it's very interesting. The change of base formula says that if I have one of these weird bases, right, not a 10, not a e, it's anything else, so log base a of m, that I can change that into a division of logs. Log of the m divided by the log of the a. And the reason that's preferable is because log, as in the common log, is in your calculator. Okay? So you need to be really careful, because if something says to show it by hand and you're doing this with the change of base formula, that's not by hand. You're welcome to use change of base formula to verify things and to confirm correct answers, that kind of stuff. But this is not showing by hand. This is really just for the purpose of your calculator. Were it not for your calculator, we wouldn't do this. It would be irrelevant. Absolutely makes no difference. Okay? So, what this says is that I can take problem A and I can rewrite it. And I can rewrite it as log of the value here, 4.78, divided by log of the base here, which is 3. Okay, that's the rewriting part using the change of base formula. And then your calculator can give you an approximation, and it will be an approximation. It will not give exact answers to this, okay? So you'll have to pay attention to whatever my math lab says or whatever the directions say on the problem. If it's a quiz question or a test question, round to what? Round to the nearest tenth, round to the nearest hundredth. What am I rounding to? So for the purposes of what we're doing here, let's go ahead and round to the tenth place. So 1 decimal, okay? So grab your calculator and hit log 4.78. Press enter. Divide it by log of 3 and press enter. It's what? 1.4 if we use 1 decimal. And if it told you to use 2 decimals, you'd use 2 decimals. If it told you to use 4 decimals, you'd use 4 decimals, and so forth.
And so
Okay.
the playing field has been.
So what that means is the examples that we were doing last time, we have a way to go back and confirm using another method the approximation that we get from those answers. Okay, everybody good? Now, B is a little different because obviously it doesn't have 2 logs written there, so what do? Well,
Change it into log form.
we change it into log form, exactly. So we start with this base and we draw our scorpion tail around. So this is log base 0.23, right? Crosses to the other side of the equal sign, 18.4, and it equals x, the exponent. Now, until today, right, you wouldn't have had a way to simplify what's on the left to another version of that, right? A simplified sort of approximation anyway. But now you do. So how can we rewrite that piece on the left with the change of base formula?
Log 18.4 or log 0.23.
Fabulous. Log 18.4 over log of 0.23. And we'll still go with our 1 decimal, I guess. 1 decimal is not what I have in my notes even, by the way. You never know what the answer is going to be anyway, so we'll just make it up as we go. What would we get on this one if we have 1 decimal for our answer? I think it's, yeah, negative 2.0. The number in your calculator probably says negative 1.9816 and some stuff after that, like that. So this would round to negative 2.0. If it does say to the nearest tenth, you need to make sure that 0 is in there. Like you can't just say negative 2. It will fuss at you for that, okay? Any questions on that one? Okay. Couple more. I think this is it. You guys ready for this to be it for today? Awesome. Okay. This feels a lot like the last problem, right? Yeah? So we're first just going to rewrite it. There is one change at the very end that's happening here that we didn't have, so be careful. So this would be log of 1 with base 1.025. We cross to the other side of the equal sign, so we hit the number 3. And it equals the exponent 12t. How is this different than the last problem besides just, hey, the numbers are different?
Divide by 12 at the end.
I need to divide by 12 at the end. Do you see the 12t? Okay, so I'm still going to change this to the log formula, right? So this is going to be log of 3 over log of 1.025. Like we're going to get that value equal to the 12t. So go ahead and get that value and just press enter. And we'll write down a few decimals for now, okay? So let's just say 4 decimals for the moment. What is log of 3 divided by log of 1.025? Let's use 4 decimals. 4915. Fabulous. And this equals 12t. And so then, like you guys have already said, our next step would then be to divide by 12. So take what's in your calculator and just hit division 12. Yeah, we'll still round the answer at the end to 1/10. So So t, right? T is 3.7. These are approximations. I should be writing approximations and so forth, but. Is that okay? So one slight change at the end there, that division by 12, so pay attention to that. Now D looks different because D didn't even start out looking like an exponential. Agreed? Okay. So what are we going to do on this one?
Isn't it already in the form?
Well, the problem is that while we could rewrite, so let me answer Damaris's question first, then we'll talk about the moving the x. The problem is if I take my change of base formula and I apply it to the left-hand side, because it already looks like, the base and the difference, is that then I've taken my base of x and now it's stuck inside of a log still. And I really need that x to be not inside of a log. I need to switch it to exponential form. Yeah, so we're going in and out of exponential and log forms sort of, it's not willy-nilly. I mean, like we're doing it with a reason, but we're doing it fluidly. So sometimes we need to be in exponential form, sometimes we need to be in log form. We need to be able to go back and forth as needed. And the reason it's needed here is because right now that x is sort of embedded, and I can't get it out unless I change it into exponential form. So I will rewrite this as x to the power 2.3 equals 12.33. And I realize this doesn't feel like the other ones at all, but it still gets thrown in this section, okay? I don't have a change of base formula here that I can apply or anything like that. So pretend for a moment with me, what would I do if this simply said x squared equals 12.33? You take the square root, right? Okay. But a square root is the same thing, like square root of x is the same thing as a power 1/2, right? Okay, everybody good so far? Okay, well, but I don't have a power of 1/2 or 2, in particular 2. I don't have a 2, but I have a 2.3. So here's what we do. Let me just give myself some space. We raise this on both sides to a power, and it's the power 1 over 2.3. Your calculator can do all this just fine, so you don't have to worry too much about that. 1 over 2.3. Right? It would be 1/2 if it were a square root, right? A square root would be the equivalent of a power 1/2, but I don't have a 2. I have a 2.3, so I don't have a 1/2. I have a 1 over 2.3. Okay, so on the left-hand side, these cancel. That's the whole point. I have x left on the left. And your calculator will allow you to put this in, and here's how, typically. So some of you have a calculator where you have like a caret key when you want to put a power. Who has caret keys? Okay. Some of you guys have buttons that say y to the x like this. Who has those buttons? Do all of you have caret keys? Okay. Cool. If you're not sure how to do this after class, you flag me down so we can make sure to look at it on your calculator. So you're going to do the caret key, and then you're going to put a parenthesis, and you're going to write 1 divided by 2.3. That's how it goes into your calculator. Okay, so everybody try and find that on your calculator screen. If you're not finding it, we need to chat so we can figure out your calculator. We'll still just do 1 decimal for now, because I gave that instruction at one point. But is it 3.0? Yeah, with 3 decimal or with 1 decimal, 3.0. Because I have written down 2.98 actually, because I had 2 decimals when I did it the last time. So yeah, so whatever the decimals are, in this case, 1 decimal. Now, let's just check to see that we can make sure it makes sense. I want you to use it because we're going to use our change of base formula to check our answer. Because I told you we would be able to check some answers. So let me cut this out just a second. So we're going to take this expression. We're going to put the 3 in for x. Okay? So, sorry, that's super bright after that darker screen. So we have, what we're checking is that log base 3 of, what was my number? 12.33. 12.33 will actually give us whatever was on the right-hand side. This should be approximately 2.3 if we've done it right. Well, you can use the change of base formula on this side, right? Sure. Log of 12.33 divided by log of 3. And if you press enter, does it in fact equal approximately 2.3? Yeah, it will. But that's how you can check to make sure that you did it correctly.
That's insane.
Isn't that great?
Maybe 2.28.
Okay. What was it?
2.28.
Yeah, because we rounded, so that happens. Okay. Wow, we're done a little early today, so don't spend all your time in one place, or maybe you should, I don't know. If you do have problems with the calculator, check in with me before you leave, though, so I can make sure and show you how yours works if it works any differently, okay? Have a great evening, and I'll see you guys tomorrow.